So picking up where we left off, we've now got a question that says sketch the graph of this function, but also clearly indicate the axis intercepts. So what that basically means is when you're finding the x-intercepts, you are solving for y equals 0. Okay, so finding the roots. So first thing we're looking at, well, the base graph is going to look like that. Y equals sine x. Okay, we know it's going to be moved up 1. So we can say we're only going 0 to 2 pi, so we're only interested in that bit. So it goes up to 1, goes like that, and it's going to go to there. Okay, so that's 1 there. This is obviously going to be 1 plus root 2, okay, because we've stretched it. So we can say 1 plus root 2, and this is going to be 1 minus root 2, and you can leave it like that, just in exact form, that's probably easier. So now we need to find out what these points are, because we know this one, we know where that was. That was your pi on 2, that's pi, sorry, 2 pi, sorry, that's pi there, and that's 2 pi, so we know that the solutions have to be somewhere in between. So to solve it, we want to let y equal 0. Okay, so if I turn that round, I'm going to write root 2 sine x plus 1 equals 0. Bring this over the other side. Root 2 sine x equals minus 1. Sine x equals minus 1 on root 2. Now we recognise that from our exact values as x being pi on 4. Okay. At this point it's a good idea to do a quick unit circle sketch. Okay, if sine of x is minus 1 on root 2, it's going to be down here. Okay, negative y values. And we know that the equivalent acute value of the angle is pi on 4, so this is pi on 4 and this is pi on 4, which means we're coming round to 5 pi on 4 there, and then all the way around to 7 pi on 4 there. Okay, so we've got our values are going to be 5 pi on 4 and 7 pi on 4. And if we look at back over here, that makes sense because those values are between pi and 2 pi. Okay, so then we can put that in here. That's 5 pi on 4, and that point there is 7 pi on 4. So you can see why you need to allow yourself lots of room. It tends to get a little bit messy once you start writing in all your intercepts and things in terms of pi and fractions and so on. Okay, so the steps there were pretty much the same. Draw your base graph, work out what your transformations are, pop those in, and then look at labelling your intercepts. And if we're being strictly correct, you do them as coordinates. Okay, so x-intercepts and y-intercepts there, over the given domain. Okay, let's have a look at a tan graph. So tan graphs are a little bit different. The base graph of tan, remember, goes from, so it looks like that. You've got repeating asymptotes all the time. Okay, and it goes, keeps going. Alright, this is one cycle here, and that's pi. So the period is pi. Okay, that asymptote is going to be at pi on 2, and so on. So you can work out where the rest of the features are from that. Now this one, this vertical dilation is just going to have the effect of stretching it up. It really just means that it makes it look steeper. You don't really have to worry about plotting points on it to show how much steeper it is. And because you don't have maximum or minimums, it's sort of a little bit harder to define, but it's going to make it steeper. This is your horizontal dilation factor of a half. Okay, so we're squishing it in. All right, so if you had pi here, applying this means that you're going to have a period of pi on 2. Okay, so this will become, and we're also going from negative pi to pi. All right, so pi on 2. Well, let's go. That's pi on 2. Make that pi. Okay, and this will become pi on 4. So you've got an asymptote of pi on 4, and then an asymptote at 3 pi on 4. Okay, this is coming through like that. This is coming up to here and stopping there because that's pi. Okay, this is going up like that. You've got asymptotes here at negative pi on 4 and negative 3 pi on 4. Another cycle here, and then from here, just like that. Okay, and wanting to label most of those. So this is x, equals pi on 4. Okay, x equals 3 pi on 4, there are your asymptotes. This is going to be pi on 2, your intercept. Obviously that's a 0, that's negative pi on 2, it's symmetrical. Okay, because you haven't shifted either way, and so on. So x is minus pi on 4, minus 3 pi on 4. Okay, probably should label these as well. So we've got x and y. Alright, so that's how you work out tan. So the only difference with tan, I mean other than the shape, is that the period that you start with is pi. So it's a good idea to make sure you remember that, otherwise you might get a little bit unstuck when you're trying to work out where your sketches go. Okay, and the last example, we're sketching this, and we also want to work out where our intercepts will be for this one. Okay, so again, we're starting with our base graph. Now we don't have a vertical dilation, we've only got a horizontal dilation, so it's just kind of squishing it in a little bit. Okay, so, and again we're going from minus pi to pi. So if we just do our first bit, okay, so 2x looks pretty much the same as the last one without the vertical dilation of 3. So we've got pi on 4 there, 3 pi on 4, coming up like that to there. Okay, same again. Like so. Alright, so you've got x is pi on 2, sorry, pi on 4. X is 3 pi on 4. Okay, and now this bit is just moving up plus 1. Okay, so if you sketch that again, so putting in your asymptotes first is always a good idea, gives you boundaries, but now we're up to here. So this will go through there. All your x-intercepts are moving up to that line there, 1, which means obviously your new x-intercepts are going to be something different, which is what we're going to work out in a minute. So we're going up here, like so. Oops, should go through there. This one starts up here and goes up there. Okay. So we've got the same asymptotes, but to work out what are our x-intercepts, so x-intercepts are when y equals 0, so again we'll do our tan 2x plus 1 equals 0, so tan of 2x equals minus 1. Now again, quick sketch of the unit circle. Okay, when tan is minus 1, we're talking about these values here. Okay, that's tan is minus 1 around there, and we should remember that the acute angle again is pi on 4, or 45 degrees. So the angles we're looking at for this one are 3 pi on 4 and around to 7 pi on 4 there. Okay, now the trick here is you've got 2x in here, so what we've just worked out is that 2x is 3 pi on 4 and 7 pi on 4. Alright, but we want to find out what x is, so you can just divide both sides by 2. 3 pi on 8, rather, and 7 pi over 8. Alright, so that means this is going to be 3 pi on 8. This one's going to be 7 pi on 8. Again, quick check makes sense. If this is pi, makes sense for that to be 7 pi on 8. Okay, remember this is pi on 4. Okay, so it fits in with what we've sketched so far. So just always do those checks for reasonableness. Make sure you're in the right kind of area. Okay, this one's going to be minus pi on 8, because you can see they're repeating every pi on 2. Okay, so you just work it back. And you can work out what the rest of those values are as well. So you label all your asymptotes, label all your intercepts, just a periodic function. Okay, and that's how you sketch your graph of tan. So in summary, transformations apply to trig functions just as they do to polynomials and other familiar functions. So if you got comfortable doing your vertical and horizontal dilations and translations with polynomials, then the same principles apply. Okay, be careful of order. Always make sure that you've got that sorted out which one you're doing first. Okay, when you're sketching, I like to start with the graph of the base function and then apply the transformations. Obviously, as you do more of these, you get better at it, and you probably wouldn't need to do that. But you know, it's a good place to start from, and it's also a good fallback if you sort of get into an exam or a test and you're panicking a little bit. Start with your base function. Okay, this is assuming that you don't have your calculator and that you're doing these by hand. Remember, if you're asked to describe a transformation, you must specify direction and magnitude. Okay, that's really, really important. If you just say it moves left, that's not enough. You need to tell me how far it moves left. If you just say it's dilated vertically, that's not enough. And remember, be careful about your language when describing dilations. Okay, you're talking either a vertical dilation or a dilation parallel to the y-axis or a dilation from the x-axis. Don't be tempted to use words like in, over, along, around, about, of, and other confusing, ambiguous sort of terms. Okay, make sure it's really clear what you mean. Phase shift, so the term phase shift refers to horizontal translation, specifically of trig graphs. Okay, when you're sketching trig graphs. And the last thing is just remembering your important features. So include x and y intercepts, turning points, that's for sine and cos, and asymptotes for tan. So make sure that you've got all those on your sketch, and then you will maximise your marks.